Welcome back. Welcome to week 12 lecture 2 of probability theory with actuarial applications. In the last lecture we have completed halfway of the course, which is up to week 5. In this week we are going to start with week 6. So we will deal with the big picture. Basically we will deal with probability models which are quite prominent in actuarial applications. Let us begin. So what we did in the last, we actually reviewed the probability toolkit. Then these were the fundamental building blocks. That means we studied PMFs, PDFs, CDFs, joint distributions and transformations. Now actually what happens is we have to understand this and assemble these pieces together to have some transformatory knowledge. That is what our today's goal is. We will review how we assembled those tools into sophisticated models that actuaries can use in a day-to-day life. So what was our boss problem that we spent our half a course on? That is basically we had a random sum S which was quantifying aggregate loss of the insurance company or the aggregate loss of the portfolio of the insurer, and it was random sum summation over I equal to 1 to n, I equal to 1 to capital N, where this summing variable is also a random variable. We called it as frequency variable, right, and this yi's are the insurer payouts. So with all these in mind, we developed this theory, and what we got finally, we were able to solve this problem, which is the aggregate loss problem. We were able to approximate the distribution of S, and therefore we were able to solve the problem and define what is the expected insurance premium that the insurance company should take from the people, right. So coming back to our review job, which is week 6, where we started with week 6 with these power tools. This one is law of total expectation and this one is law of total variance. So what was our goal? Our goal was to find the expected value of y and variance of y by conditioning another related random variable x. Therefore we introduced something called Tower property. What was the Tower property? Given y, I want to compute, let us say I want to compute expected value of y, but what I will do, I will slice this y in terms of expected value of y given my x, okay, and then what I will do, this particular thing we have defined in a rigorous manner, that this particular thing is actually a function. This expected value of y given x is actually treated as function of x, and now what I will do is I will take expected value around this, which will give me expected value of y. So essentially what I am saying, this is expected value of gx. So this is the way we built the tower, and therefore the other name to finding this expected value of y via random variable x, which was somewhere related, we call this as Tower property. So that was the name that we have given, Tower property. And in particular, if I want to state it formally, the law of expectation is stated like this, right. So whenever I take a realization of x, this is like saying I have sliced y with x is equal to x on that probability distribution, and then I am taking the average, right. So what I am saying here is the law of total expectation is expected value of y is expected value of y given x, and when this becomes g of x, you are taking another expectation of this. So this expectation is with respect to x, this expectation is with respect to y, okay. So this is, so the overall average which we talk about is expected value of y is the average of specific averages. What are those specific averages? Gx, okay. So this is law of total expectation. building on this, we have explicitly derived something called law of total variance, and that law of total variance is very special. We called it Eve's law. What is Eve's law and why we call it as Eve's law? Let us define it in a way. Say I want to talk about variance of y. Now if you look at our problems, for example, when I talk about S, it was sigma over yi, I equal to 1 to n, where the variability is coming in two forms. One is this variation, which is the variation in the frequency. Another one is this variation, which is variation in severity. So what I need is, in this case, how will I handle the variances, because there are two forms of variances. So this law of total variance that we derived is a significant help for us to get to it, because when I talk about this, I am talking about this variance of y given x, okay. And then what I will do, so as I mentioned here, the overall average is average of specific averages. In this case, what I have done, I have taken variance of specific random variables, and what I will do then, I want to get the aggregate variance, right. So I will take expectation of this. That is the beauty. Am I done? No, I am not done. Why? Because I have just coined variance. What about variance of these random variables, these slices? I have taken expectation. What about variance of these? So that is where the next term in this law, which is you take the average of specific averages, expected value of y given x, and this, as you know, is a random variable in x. So I have to talk about variance of it, right. So that is where my Eve's law comes. So this is one E, which stands for expectation, this is one V, which stands for expectation, and this is average of random variables Eve, okay. So that is how the terminology Eve's law is designed. So what is it? It is a joint venture of two variances. In this case, it is a joint venture of n and yi's. So we can easily see that this first term is actually the average risk which is there within the groups, the variance of individual random variable y given x, and then I take expectation of that, and the next one is risk between the groups. So intra group, the risk or the variance that you are trying to average out, okay. So this is a wonderful toolkit that we have, law of total expectation and law of total variance. Now how will I apply these toolkits, right? So that is where we developed some probability models. Typically I showed you one model which is a random sum, another one is a mixture model, and that is what we did in week 6. We took two kinds of models, one which is a mixed model where we are actually considering the parameter itself is a random variable. So this mixed model actually takes parameter as a risk, and therefore we are evaluating the parameter risk. Therefore expected value of y is expected value of y given theta, and the variance of this will be, again I am simply applying these formulae and getting this these answers. So it is variance of y given theta, and this is among the groups, and you average it over, and then this is variance between the groups, right. So we are actually finding out averages, and then we are computing its own variance, okay. Then we came to our standard problem, which we called as Boss problem or compound model, where we dealt with this aggregate loss distribution. And now we have I equal to 1 to n, and this n is a random variable, right. So this is the compound sum, and then we coined these terms. For example, we were conditioning on n, So, in that expected value of y given x, we were identifying s with y and we were s with y and we were identifying n with x. Okay. So, these are our identifications, and once we identify that, then you can easily see this becomes the formula for our law of total variance, and this becomes the formula for law of total expectation or the Tower property. However, when I have Poisson random variable, expected value of n is actually equal to variance of n. So, in that case the formula actually simplifies because both are same. Let us say that we call them as lambda, then you put lambda here, and then what happens, variance of y plus expected value of y squared. So, you open this variance of y, it will be expected value of y square minus expected value of y the whole squared, that takes away this particular y, and therefore finally what you are left with, a lambda multiplied here. So, lambda times expected value of y squared. That is the beauty of this formulation when I have a compound Poisson distribution, correct. So, all these things are good. So, what we were able to achieve up till this point is we were able to quantify for mixed models and compound models what are means and variances. But what about, I want to know the full distribution, and mainly our distribution comes in the form of random sums, right. So, is there any intelligent way to capture this convolution or the sum, okay, independent sum? So, we tried to answer that in our week 7. What did we do in week 7? We derived a tool called MGF, and then successively we derived a tool called cumulant generating functions, CGFs, right. So, what we were doing, if you remember, we were struggling in week 5 to get the full distribution of random variables of the form x plus y. So, we tried to do these transformation techniques and we got some results. However, the problem was you have to integrate lot of things. For example, two normal random variables are given. If you are taking their densities and you are putting them in the convolution formula, the integrals may become messy, right. So, is there any easy way out? The answer was given by MGF, which is moment generating functions. So, here the key idea is MGFs are actually the functions that are transforms and that will generate moments. So, these are the key properties of MGFs, where if I want to compute expected value of x raised to k, I will take moment generating function. Let me define that moment generating function, as I have not defined yet. It is expected value of e raised to tx, where what is the freedom or leverage that you have? This free parameter t, okay. And then we actually figured out how to compute these moments. So, essentially what is happening, this mxt should exist in some neighborhood of 0. If it exists, then you can actually differentiate this function as many times as you want. If you want to compute kth moment, you differentiate this function that you got at k times and put the value of t to be equal to 0, and you will get expected value of x raised to k. Then what we did is very interesting thing, which is basically we mapped moment generating functions in one-to-one correspondence with either probability density functions or probability mass functions, and we designed one lookup table. For example, if you ask me what is a moment generating function for a Bernoulli random variable, then I can write 1 minus p plus p e raised to t. Okay, this is a Bernoulli random variable. If it is a binomial random variable with parameter np, it will be n. So, this is my moment generating function, right. Similarly, you will have different moment generating functions. All those were discussed in this lookup table, where we had seen moment generating functions of discrete distributions and continuous distributions. Once we have this clear cut mapping, we came to some properties of these moment generating functions. So those properties essentially means, if I have a sum and they are independent, if x and y are independent, then the moment generating function of the sum is actually product of the two moment generating functions. So this was significantly helpful. For example, if I have x which follows Poisson with parameter lambda 1, y which follows Poisson lambda 2, then I am interested in knowing the distribution of x plus y. How will this formula help? If x follows Poisson lambda 1, do I know what is its moment generating function? Yes, I do know. It is e raised to lambda 1 t minus 1. Okay. And if it is Poisson lambda 2, it is e raised to lambda 2 t minus 2. Okay. Sorry, t minus 1, sorry. You can easily verify this. Then by this property, what I know is this will become e raised to lambda 1 plus lambda 2 t minus 1. Okay. And therefore, what I can say, because of this property, and now you can convert it into this, there is a one-to-one correspondence. So what will this be? I also know this is going to be Poisson with parameter lambda 1 plus lambda 2, right. So this is very easy for me if I have this particular mapping. So this is how I or we were able to solve all the problems related to sums simply by taking products of independent random variables or product of independent moment generating functions. Then some of the messy parts came, where I had to deal with something like e raised to minus t square by 2. Remember, this is a moment generating function of a standard normal random variable. So what we did, we devised a methodology where I can get rid of these e raised to things, and a natural answer to that is taking natural log of this. So this will essentially give me minus t square by 2, right. So e raised to t square by 2, e raised to t square. So this will naturally give me this particular thing, and that is where the next thing, which is CGF, cumulant generating functions, came into play. So what is a problem here? Here I had products. Now I want to get rid of products and I should treat sums for sums. So what I can do is, I will simply take ln of this, I will simply take ln of this, and what I get, if I take these ln's, what I get is a simple formula for this. Okay. Now came our boss problem, which is the compound sum. And can I have a similar flexibility for solving the compound sum problem? The answer is yes, I have, and that is where we derived this compound sum MGF, which is essentially Mn. This is the moment generating function with respect to n, where the argument is ln of mxt, which is the cumulant generating function again. And therefore, as you can see, I have already done for Poisson. So now you can see this Poisson shortcut, which is the compound Poisson thing, which essentially turns out to be e raised to minus, so that mxt mxt is replaced by t, ln of mxt is replaced by t, is e raised to minus lambda t. So this becomes e raised to lambda mxt minus 1, which is similar to this. So t is replaced by mxt here, okay, and that actually solves my entire problem of understanding the distributions, right. Now we understood how to consider sums, how we can handle them effectively using moment generating function or cumulant generating function. But to compute the actual probabilities, these things are not helpful. So what can we do? Therefore, if somebody gives me some information about moments, what I can do is, I can best approximate those probabilities, and I want to use the information about those moments while approximating those probabilities. That is where we ventured into a tool called inequalities. So, this is the tool that we studied in week 8, where we actually wanted to have some quantification of probability, and maybe it can be a worst bound, but I should have that bound. That is where I have a global picture. So, we pondered on that and we derived few important inequalities, which are: first, if I have a non-negative random variable and I know expected value of x, what can I do to tame the tail probabilities? The answer to that was yes, you can do something. If you want to compute probability of x greater than or equal to a, if it is a non-negative random variable, then I can simply estimate it to be less than or equal to expected value of x by a, where obviously a will be greater than 0 because we are talking about a non-negative random variable. Okay. So, this gave me some crude bound, some very vague bound on expected value of x. Let us understand it in this way, that if my expected value of x is say 4, okay, and I am asking you a question that what is the probability that x is greater than or equal to 8, what should I answer? So, the answer to that is, this is given by 4 by 8 and that is equal to half. So, probability of x greater than or equal to 8 is actually half. Okay. So, this may not be a very accurate answer, however, I have some estimate, right. So, the next question is, in general in science, when you derive certain bounds, can I improve this? Can I relax this condition? The answer is yes again. So, what will we do? We will consider, by relaxing the assumption, what we will do? We will center this around the mean. That is what we did when we talked about x minus mu greater than or equal to k sigma, and then we said this is less than or equal to 1 by k square. This is an interesting thing, but it is direct implication of this Markov property. With the more information that is given, mu and sigma square. Here I had only mu, here I have mu and sigma square. So, how can I derive? We have derived this, but let me give you a glimpse of this. So, what I want for Markov, I want a non-negative random variable. X now is not a non-negative random variable. So, what I can do is, I can consider x minus mu. This is also a non-negative random variable, but if I consider x minus mu squared, okay, x minus mu is also not a non-negative random variable, but if I consider x minus mu squared, this is actually a non-negative random variable. Okay. Then for Markov inequality to be applied, what I need is expected value of x. So, what is expected value of x minus mu the whole squared? It is actually sigma square. Do I have that information? Yes, I have that information. Now, what I can do is, I will essentially map this x minus mu square greater than or equal to some k square, let us say some k square, or to be precise, you can say some a squared. Okay, I am asking this probability. I will apply this Chebyshev inequality, right, and I will get what? I will get this to be less than or equal to sigma square upon, this is expected value of x, right, sigma square upon a square, correct. So, you understand the beauty of this. Okay. Now, I have sigma square a square, but what is this set equivalent to? This set is actually equivalent to probability of mod x minus mu greater than or equal to a, correct. And now I am saying this is less than or equal to sigma square by a squared, perfect. So, now what if I put this a to be equal to k sigma? if I put A to be equal to k sigma, then what I got, probability of mod x minus mu greater than or equal to k sigma is less than or equal to sigma square upon k sigma the whole square, right. So, sigma square gets cancelled, you get this inequality, right. Now, logical equivalent of this is, if I consider probability of mod x minus mu less than k sigma, what will I get? Because this is less than or equal to, this should be greater than or equal to 1 minus 1 by k square. So, what I got effectively, using the same Markov inequality, I got another inequality which is called, attributed to Chebyshev of course, because he figured out another inequality which is valid for any random variable and which is giving me more precise bounds, because this controls the second moment. So, the bounds will be more precise. Okay, so that is our Chebyshev inequality. Then came another interesting inequality, because some people say that okay, but still I have only positive random variable or I have only negative random variable, then these bounds are somewhat vague. Then came another interesting inequality which is one-sided Chebyshev, and this proof is slightly tedious, so we skipped. I will again skip this proof, but it conveys an important message. Basically it says this particular thing, which is essentially probability of x minus mu greater than or equal to a, that is the idea, that is the cornerstone, is going to be less than or equal to sigma square upon sigma square plus a square. Okay. So, this is one-sided Chebyshev. Now comes the interesting question. So, you have bounds. Suppose like in Chebyshev we have shown that this is 1 by k square. So, this, as this k increases, naturally this bound goes to 0, correct. As this k increases, this bound goes to 0. Now the question comes, okay, then what if I have some random variables which are like IID family x1, x2 and so on up to xn, and I am looking at a new random variable which is x bar, which is 1 upon n sigma xi, and now I want to talk about this random variable which is x bar, and I feel because it is going to 1 by n, this random variable has mean mu, variance sigma square. What will happen to the variance of x bar? Okay. Then I can see variance of x bar will actually be equal to sigma square by n. Is it clear? Why variance of x bar will be sigma square by n? Because xi's are IID, they are independent and identically distributed, and if I take variance of sum, it will be sum of variances. So, all sigma squares will come, okay. But when I throw something out of the sum, it becomes 1 by n squared, the quantity becomes squared, that is I am appealing to variance of Ax is equal to a square times variance of x, okay. So, in this, therefore, what happens, this becomes, so in this particular case it is 1 upon n sigma xi, right. So, when I throw this 1 by n out, it becomes 1 by n squared summation over variance of xi's. What are those xi's? Xi's have variance sigma square. So, this becomes 1 by n square sigma square, right, I equal to 1 to n. So, this essentially, because it is a constant, this essentially contributes to n, and therefore, this n takes away this n, and therefore, what I get is variance of x bar is sigma square by n. Now, you apply this Chebyshev inequality to this particular terminology. What you get is, so I have applied probability of mod x bar minus mu greater than or equal to say k sigma. Okay, what is sigma here? Sigma is this, but now I have sigma square by n, so it is sigma by root n, okay, and then what I got is less than or equal to 1 by k square. But you can see this thing 1 by k square is very small and I can choose any k as small as I like. What is the impact of this n? This n is actually as this n increases is actually shrinking this particular number as well. You choose this k to be fixed, but this number is fixed, interval is going smaller and smaller, and therefore what I have is a different version of this, which is essentially if I want to replace this with something like probability of mod x minus mu, x bar minus mu greater than or equal to epsilon, okay, and then based on our Chebyshev inequality, this is going to be variance of x bar upon epsilon square. So, no matter how small is this epsilon, what is variance of x bar? This is going to be sigma square by n epsilon square. So, what does this mean? For any epsilon that is greater than 0, I am getting this number which is shrinking to 0, and that essentially leads to an important innovation, which is law of large numbers using Chebyshev, and we say that xn bar converges to mu, and this essentially guarantees that insurance pooling works. That means many insurance portfolios or many insurance policies taken together will actually give me a stable mean, a constant mean, and that is the beauty of this particular structure. Okay. Once I have this, then what we did, okay, so we were able to approximate the probabilities. So now we need to actually go for estimation of the parameters, so estimation tools. So for tight estimates for probability, we can do something like first, which is Poisson approximation. We dealt with this in detail, where p's are small, you are essentially approximating NP, which is approximately equal to lambda, and if p is becoming smaller and smaller, then this approximation actually works better and better for n large and p small. So, this is where we had a beautiful thing, and then what we did is the next tool, which is very important and which was the cornerstone of our solution to Bose problem, was central limit theorem, where we actually figured out if I have any distribution x1, x2, xn, these are coming from some distributions, only thing I need is they should be IID and they have some f, which is the density fx, you can call it. I do not care, as long as they have finite mean mu and variance sigma square, I can use this tool and I can say my xn bar, which is this is the case, minus mu upon sigma over root n will go to normal 0 1. This is the essence of, and we called that as convergence in distribution. We did not dig deeper into these concepts, but we were pretty familiar with these concepts, and therefore what we are saying is my xn bar actually approximately follows normal with mean mu and variance sigma square by n. That was the idea about around central limit theorem. I can rephrase this in terms of Sn, and if I reframe this in terms of Sn, this is xn bar is 1 by n, so I have to multiply by n, so it is minus n mu upon root n sigma, okay. So this will actually converge to a standard normal random variable, and that is what I mean when I approximate this Sn, I will have Sn which is approximately normally distributed with parameter n mu and variance n sigma square, and this approximation is roughly applicable for about 30. If the distributions are very skewed, only one sided, then you may go to 60 or 100 iterations to get these better approximations. So that was our tool 2. Now the idea is, what we are saying in central limit theorem is very wonderful. No matter what the distribution is, you are essentially able to approximate it with normal distribution. But this raises an important issue, because if I consider a Poisson random variable, what is the meaning of probability of a Poisson random variable equal to 4.5? It does not mean anything, right? Okay. So in such cases, when we are approximating it with continuous distributions, you need to attribute that meaning to it, because when I talk about probability distributions, if it is a discrete random variable, I talk about probability mass function, and if it is a continuous random variable, I talk about probability density function. And now if I am approximating it by a continuous random variable, then I have to somehow make a meaning of probability density function as a probability mass, and that is where the key notion of continuity correction comes, right. So when I approximate something greater than or equal to k, then what I will do is, when I am normalizing, I will subtract a 0.5 mass from it, okay, and we have solved many examples related to that. So this notion is very clear. Similarly, I will have less than or equal to k, and then I will take, because k is included, k plus 0.5. So all those things are essentially part of our approximation structure, okay. So now let us move on and see what we have built in week 10 and 11. So we basically developed a master algorithm, and we have devoted several classes or several lectures for computing these things: expected value of S, variance of S, and then approximate probability of S greater than or greater than k. So how to do that? So for that we have a master algorithm which essentially has 5 steps. So first thing was finding the moments of n and x, which we are very much familiar with, it is a straightforward thing. Then relate it to insurance policy. So we want insurer payout. So you have to essentially compute expected value of y and y square. What are y's and y squares? Depending on what policy we are applying. So here is an example of a layer policy where I have deductible and the upper limit together. So we can figure out how to compute expected value of minimum of x and u minus expected value of minimum of x and d, okay. So that we have seen in detail. Once I have this particular thing, which is essentially expected value of y and y square, which of course I will compute via Lotus, law of total variance and law of total expectation. Then I will talk about moments of S, where I will use expected value of S as LTE, or law of total expectation suggests expected value of n into expected value of y, variance of S, which is expected value of n into variance of y plus variance of n into expected value of y square, and then you have these two moments. The key problem in that case was I do not know the distribution of S. So what we did, we used these two calculation of moments and approximated the distribution of S by a normal distribution with these two parameters, and then you can easily solve all problems like expected value of S, variance of S, which is already known to you. You can easily, because of this approximation, you can easily compute probability of S greater than k by standardizing this random variable using this mean and variance which we have computed, and then by after standardizing you can see the normal lookup table which is called Z table, and essentially before doing anything conversion to Z, or before seeing the probabilities, you check whether your severity is discrete or continuous. If it is discrete, apply continuity correction. If it is continuous, no need to bother about continuity correction, and compute the answer. That is the idea, and this was our entire course. So, let me summarize what we have done. So, in the last lecture we have reviewed this probability toolkit which was weeks 1 to 5. In today's class we have done weeks 6 to 11 where we have solved the boss problem virtually, and now what you are ready is you can actually acquire the knowledge of these models, assemble the pieces together, comprehend properly, because now you have all the knowledge required and now you need to practice solving the problems, right, and you have to solve these problems in minimal amount of time. That is where our final step comes. You have to practice and speed up. So, what we will do in the next lecture is we will share with you a full question paper, a 30 question mock exam. Before reading or before listening to the next lecture, you try your hand on all those problems. You should have your own synthesis of those problems and mark how much time you required. Okay. Once you have done that, what we will do is we will go through those questions one by one, and in a span of 3 minutes I will tell you all the tricks and tips to solve each and every problem, which will no longer require more than 90 minutes. So, before watching the next lecture, you should take that time test of 90 minutes and see how many problems you were able to solve, and given larger amount of time you can also try to solve these problems and record the timing that is required to solve each and every problem. Once you have done that, come to my next lecture and see how you are performing. Okay. See you in the next class. Thank you.